Welcome to the series of lectures on finite element analysis. In this part, we are going to start the finite element method, what are the various finite elements available, and how to apply these finite elements in solving the engineering problem. In the first part, we have discussed about the basic concept of FEA, that is how FEA works. So with a simple example, for finding the circumference of a circle, we can approximate the circumference of a circle by assuming the number of chord length. So that is, the given circle will be discretized into the number of sector. For each sector we will draw a chord length, then that chord length will be defined. After knowing the length of the chord line, then we will assemble all the chord line to get the approximate value of the circumference of a circle. So this is the basic idea of finite element analysis. In finite element analysis, any structure will be discretized into number of substructure. Then in the substructure level, we will try to solve the problem. After getting the solution in the substructure level, then we will assemble those solution to get the solution for a structural level. This is the basic idea or concept of finite element method. When you divide the complex structure, we are getting number of substructure. That substructure is called element or finite element or simply element. These elements are connected at critical points called node. So in this example, if you take this chord, each chord line, this is called element. These adjacent chord lines are connected at the points called node. So the node is maintaining the connectivity between the adjacent elements. So this is important, we have to understand. Either the element may be any type, but the nodes are connecting the adjacent elements properly. So now with this idea, we will go to the various types of element and how to use these element we will see. So in the finite element method, there are different types of classification for finite element, but the major classification is based on the dimensions of the element. So one dimensional element, two dimensional element, and three dimensional. This is the major classification. How these elements are classified means, in case of the engineering problem, if the variable, the field variable is varying along only one direction, let us say x direction, then we have to use one dimensional element to solve the problem. The examples are rod problem, beam problem we are going to discuss. So in case of taper rod problem, what we discussed in the Rayleigh method and weighted residual method, load is acting on along the axis direction, and also the deflection of the bar also happening along the same axis direction. So in this way, both load and deflection are acting in the same direction. Then that type of problem can be solved by using a one dimensional element. Then if the variable, that is the deflection or displacement, is changing in two direction, x and y direction, then we have to use the two dimensional element. So best example is any plate which is subjected to biaxial stress condition. That means a load is acting both along the x direction as well as y direction. So this is called a biaxial stress system. For this type of plates or structure, we have to use only two dimensional element. Then only we can study the behavior of this material under this load condition properly. Because in this application, when we use the one dimensional element, we will not get the correct result of this problem. Selection of the element is very important in case of finite element method. So that is based on the experience as well as the knowledge of the problem. The main thing to decide the selection of element is how the field variable is changing in the structure. If the field variable is changing in all the three directions, x, y, and also in the z direction, then we have to use the three-dimensional element. So the common three-dimensional elements are tetrahedral and rectangular prism element, or it is also called brick element. For any element, if you want to apply that element for the particular application, first we should know what are the basic characteristics of that element. Based on that only we can decide whether this element can be useful for that particular application or not. So first we will start with the one dimensional element. After completing the application of the one dimensional element, then we will take up the two dimensional element problems. So these are the example of finite element mesh. After discretizing the structure using one dimensional element or two dimensional element or three dimensional element, after discretization it is called finite element mesh. So you can see in this finite element mesh, each elements are connected by a node, that is adjacent element are connected at nodes, right? So these nodes will maintain the connectivity between these elements. That is very very important. So this is a finite element mesh formed by one dimensional line element. So this is the finite element mesh formed by two dimensional triangular element. Here the finite element mesh formed by the three dimensional brick element. Now we are going to see first the one dimensional element and its application. So what is a one dimensional element? As we discussed, if the field variable of the given structure is changing along only one direction, let us say x direction, then we are able to solve that problem by using the one dimensional line element. So why it is called line element means the shape of the element is like a straight line. So that is why we are calling it as line element. For any finite element problem, first thing we should define the position of this element. That means each element has a number of nodes. This node point should be properly defined. The geometrical position of this node point should be defined. So for that we are using the geometrical coordinate system. So as we have all discussed in our mathematics, right? So any point should be defined. The position of the point will be defined by the geometrical coordinates x, y, z, like that. In case of one dimension element, we are going to use only the one coordinate axis x. Now when you define the position of the node, so in this line element we are considering only two end node, right? So now this is the straight line, the element, and the left end the node is numbered like this, node number 1, and left right end node number is 2, and in the center there is a numbering with inside a circle. So this is called the element number. So this is a node number, this is the element number. So elements numbers are encircled one. So any number with a circle, encircled numbers are for elements, and without a circle the numbers are for represented by for nodes. Okay, so that difference you have to know. So both elements and the nodes are defined by numbers. If the numbers are within a circle, then it is a denoting the element number. Now coming to the position of the nodes. Okay, so this position of each node should be defined. If you know the geometrical position of the node, then only we can proceed the problem. So for that, if the nodes of all the elements present in the finite element mesh referred with respect to a common reference line like this, then we call that coordinate measuring system as global coordinate system. That means distance of node 1 from the reference line is x1, distance of node 2 from the common reference, same reference, is x2. Similarly, suppose if there is any other element is present here, right, the second element. So let us say this is element number 2, right? For this element number 2 we will have one more node. This node number will be 3. This second node is will be common node for both element 1 and element 2. Now in case of global coordinate system, this node number 3 is also referred with respect to common reference like this. So this will be referred as x3, right? So this is called a global coordinate system. First we will start the problem with the global coordinate system. Later on we are going to apply the local coordinate system, which is more useful for solving the finite element problems. Now in this one dimensional element defined with respect to a reference line, and we have x1 coordinate distance of node 1, x2 coordinate distance of node 2, and At each node we are going to apply degrees of freedom. So here the pi 1 and the pi 2 are called the nodal parameters given to each node. So these nodal parameters are nothing but degrees of freedom for at each node. So when we use this element for solving a scalar variable problem, then we will use only 1 degree of freedom, because in case of scalar variable there will not be any direction involved, we will use only the magnitude. So in that case we will give only 1 degree of freedom at each node. For example, scalar variable means temperature, pressure and all scalar variable. So in that case we will give only 1 degree of freedom. But when it comes to vector variable problem, we will resolve this vector into number of components, x direction and y direction, like that. So in that case we will get more than 1 degree of freedom. So for example, if you take a beam problem or truss problem, you will get the degrees of freedom for one element is u1 v1, u2 v2, like that. Okay, so that we will discuss later on. But what we have to understand here is at each node 1 degree of freedom is given, pi 1 and pi 2. Pi 1 pi 2 are common notation. It may be a scalar variable or it may be a vector variable. It's a common. So depends upon the nature of the problem. The node will have 1 degree of freedom or 2 degree of freedom, and in case of 2-dimensional element and 3-dimensional element, so 6 degrees of freedom, 8 degrees of freedom also possible. That we will discuss later on. But in this one-dimensional line element, we are assuming only two end node, and at each node we are placing only 1 degree of freedom, like this pi 1 and pi 2. So this pi 1 and pi 2 are called nodal parameter. X1 and x2 are called nodal coordinates. Now what is our objective here is we are trying to find the value of the field variable pi inside this element, right? If you take any point inside this element, now how to find the value of the variable pi within the element? For that we are going to use the concept of interpolation. That means using the values, nodal parameter values pi 1 and pi 2 and geometrical coordinates value x1 and x2, we are going to interpolate the value of variable pi within this element, right? So for that we are going to get one interpolation function. If you want to get that interpolation function for this pi of x, first we have to assume a trial function for this pi of x, then we have to apply the boundary conditions to the trial function, then we will get the solution for this pi of x. This is the usual procedure, which is called a Ritz method or nodal approximation method. So what we are trying to do here is we are going to define one finite element. When we'll say the finite element is completely defined means, if we know the value of the field variable at any point inside this element, then only we can say the element is completely defined. So for that we need a interpolation function. So that interpolation function going to be derived by using the nodal parameter and the nodal coordinates. Okay, so for that we have to use the boundary condition. We will see the small derivation. At the end of the derivation we are going to get a function called shape function. This is the derivation for the shape function of the one-dimensional line element. So now we will go through this derivation quickly. Here again I am showing this one-dimensional line element where x1 and x2 are the nodal coordinates, pi 1 and pi 2 are nodal parameter. Our objective is we are trying to evaluate the field variable pi within this element, right? So in the first pi of x is assumed as a naught plus a1x, that is a linear polynomial we are assuming. In this case we are assuming that the pi variable pi is changing from node 1 to node 2. Variable pi is changing from node 1 to node 2 linearly. So that is why this element is also called a one-dimensional linear element. So we are assuming that the field variable is changing linearly between these nodal points. Some application this assumption may be suitable. But most of the application, the field variable, say for example, maybe a displacement. So in that case, the displacement will not vary linearly inside the element. So in that case, we have to use a non-linear element. The non-linear elements are called higher order element, that we will discuss later on. So this is the preliminary stage. We are assuming a straight line element with a two end node. At each node we are assuming only 1 degree of freedom, pi 1 and pi 2. With this information, we are trying to evaluate the value of the pi of x inside the element. So for that, initially we are using a trial function. Linear polynomial is assumed here. A0 and A1 are called unknown coefficient or Ritz coefficient. So now when you write this equation in the matrix form, one equation will be converted into product of row matrix and a column matrix. So row matrix we are writing 1x, column matrix we are writing the unknown coefficients A0 and A1. So now how to evaluate this A0 and A1 unknown coefficient? By using the boundary condition. What are the boundary condition? At node 1 we know the value of variable is pi 1. This one condition. At node 2, the value of pi is pi 2. So this is the second boundary condition. Using this condition, we are going to evaluate A0 and A1. Let us see the small derivation. We are applying the boundary condition. At node 1, what is the nodal coordinate? X equal to x1. Then pi of x will become pi 1. Then when you substitute this one in this equation 1, so pi of x will be A0 plus A1 x1 is equal to pi 1. So this same thing is converted into matrix form 1 x1 a0 a1 like that. At node 2, second boundary condition, nodal coordinate value is x equal to x2, pi of x is equal to pi 2. So pi, when you write it in equation, pi of x equal to a0 plus a1 x2 equal to pi 2. So combining these two, this equation also written in matrix form 1 x2 a0 a1. Now we are going to combine this equation 2 and 3. So you will get 1 x1 1 x2 a0 a1 in the right hand side. So you will get a square matrix, and the left hand side will get a pi 1 and pi 2, right? So now let us see, combining these two equation, the left hand side we have pi 1 and pi 2 nodal parameter matrix. Then right hand side 1 x1 1 x2 square matrix. This is called the coordinate matrix. Then this is A0 A1 column matrix, unknown matrix, unknown coefficient matrix. Now our aim is to find this A0 A1 value. So how to find this one? We have to take this square matrix, coordinate matrix, to the other side of this equation. So when we take like that, it will become inverse of this matrix. So inverse of this square coordinate matrix we have to find. Once you find this inverse of this matrix, then this A0 A1 will be evaluated. So how to find the inverse of a 2 by 2 matrix? Very easy. So it is, what is the general formula used for inverse of a matrix is transpose of a cofactor matrix divided by the determinant of the matrix, right? So for 2 by 2 matrix, this can be easily solved. Here the 1 by x2 minus x1, this is the determinant of this matrix. X2 minus x1 is the determinant. And here the cofactor, transverse cofactor matrix can be easily written. We have to interchange this major diagonal element, right? X2 and 1 is interchanged, and we have to multiply with the minus 1 to the minor diagonal elements. These are the writing the inverse of a 2 by 2 matrix. Now after getting this inverse, now we know the values of A0 and A1 in terms of, you see, nodal coordinate and nodal parameter. We are going to apply this A0 A1 value in the first equation. Let us see what is the first equation. Y of x equal to 1x row matrix A0 A1. So you apply this A0 A1 value. So 1x row matrix 1 by 2 matrix. Then A0 A1 we have evaluated 1 by x2 minus x1, x2 1, x2 minus x1 minus 1 1 multiply by pi 1 and pi 2. So now this 1 by 2 matrix going to be multiplied with a 2 by 2 matrix. So resultant will be a 1 by 2 matrix like this. So 1x multiply this x2 minus 1. So it will get x2 minus x1 x Similarly, the second one is minus x1 plus x. So x minus x1. Then this matrix we are writing pi 1 pi 2. Then take this x2 minus x1 inside this matrix. It will become x2 minus x divided by x2 minus x1, x minus x1 divided by x2 minus x1. So when you take this one, pi of x equal to x2 minus x divided by x2 minus x1, x minus x1 divided by x2 minus x1, then pi 1 pi 2. This part is named as n1, this part is named as n2. That means n represents the shape function for node 1. This is shape function for the node 2. This is a nodal parameter. So pi of x nothing but the value of the field variable within the element at any point x can be found like this: n1 multiplied by pi 1, n2 multiplied by pi 2. This is nothing but we are evaluating the field variable pi inside the element by using the n1, n2 and the pi 1, pi 2. This is called interpolation. Using the known values, we are finding the unknown values. That is called interpolation. So we are interpolating the field variable within the element. Now this n1 and n2 are called shape function. Shape function for this one dimensional element. So n1 and n2 defined in terms of geometrical coordinates here. So n1 is equal to x2 minus x divided by x2 minus x1. n2 is equal to x minus x1 divided by x2 minus x1. n1 and n2 are derived based on the geometrical coordinate system, but when we solve the problem in finite element method, when we use the geometrical global coordinate system, then it is very difficult to assemble all the elements. So for that reason, they will use the local coordinate system. So most of the softwares are using only local coordinate system, which is very easy to handle the problem and also solving the matrices. So we will see what is local coordinate system and how to express this shape function n1 and n2 in terms of local coordinate system. Now you see the shape function of one dimensional element. In terms of global coordinate system, we derived the expression for n1, which is x2 minus x divided by x2 minus x1. What is this x2 minus x1 in the denominator? It is nothing but the total length of the element. x2 minus x1 is length of the element. And in numerator we have x2 minus x for n1, and n2 it is x minus x1, x minus x1. When you come to the local coordinate system, what is local coordinate system? In global coordinate system, all the nodes are referred are defined with respect to common reference, but in case of local coordinate system, each element will have its own reference line. So each element will have reference line at a left node, left extreme node. So when you have the reference line at a element itself, then your coordinate distance will be measured in terms of length of the element. So here when you place this reference line is shifted to this node point 1. This is called a local coordinate. Similarly, for each element there will be a reference line. So right, there is a next adjacent element, then we will place a reference line here. For that particular element, this will be the reference. So in that way, we can easily measure the coordinate in terms of the length of the element. Here you see we are using L is nothing but the length of the element, right? So when you place the reference at the left extreme node, your x coordinate distance will be 0, and when you come to the right extreme node 2, this is node 2, then your x2 coordinate value will be equal to L, because in the node 1 x is 0, node 2 the full length is covered, so x2 the coordinate distance will be L. Like that, for each element we can write the shape function using this local coordinate system value. Then for all the element the shape function will be common. Suppose when we use the global coordinate system, then the shape function will be different for different element, right? Because when we go to the next element, we will get the values as x2 and x3. Instead of x1, we will get x2, x3 and x1. So for each element, the expression for shape function will be different. We cannot easily assemble all those elements. So for that convenience, in finite element method, always they will use local coordinate system to define the shape function. So now what will be the difference in shape function? When you apply x1 equal to 0, x2 is equal to L, right? In this expression, x2 is equal to L, then x is minus x, so L minus x, x2 L, x1 is 0, so you will get L here. So L minus x divided by L, right? So here L minus x divided by L, then it can be easily written like this, 1 minus x by L. Then coming to this one, x1 is 0, x2 minus x1 is L, so it is simply x by L. So n1 is 1 minus x by L, n2 is x by L. Now this shape function is common shape function for all the elements present in the finite element mesh. This is the advantage of local coordinate system. Most of these softwares also using the local coordinate system only, so we can easily assemble all the element matrices if we use the local coordinate system to define the shape function. So hereafter we are going to use only this shape function in terms of local coordinate system. So n1 is 1 minus x by L, n2 is x by L. We want to use this element. First we should know the what are the shape function for the particular element. Then we have to understand the properties, important properties of the shape function. There are three properties we should know. Then first one is, mathematically it is expressed like this: ni of xj is equal to 1, where I is equal to j, it will be 1. If I is not equal to j, then it is 0. What is the physical meaning of this one? That is, the shape function will take a value of 1 on its own node. At all other node, it will take a 0 value. So this is the graphical representation. You see, this is a x1, x2, that is node 1 and node 2. This line, red color line, indicates how the shape function 1 is varying from node 1 to node 2. Blue color line is representing how the shape function 2 is varying. At node 1, n1, shape function n1 takes a value of 1 and it is varying linearly, and it takes 0 value at the other node. When I is not equal to j, 0. Similarly, n2, shape function n2 takes a value of 1 at node 2 and it is varying linearly it varying, and it takes 0 value at node 1. Why we are assuming linear variation? Because we assumed linear polynomial. I think you remember this n1 and n2 are defined based on the polynomial a0 plus a1x. We assumed that linear polynomial. That is why the shape function n1 and n2 are also vary linearly. This is one important property. If you take a point on this element here, right, which is very close to node 1, then if you see the contribution of n1 and n2, this is this contribution of n2, this is contribution of n1 shape function. Similarly, when you take a point which is near to the node 2, then draw a vertical line. Now this is the contribution of node 1, this is the contribution of node 2. That means if the point we are considering within the element is closer to the node 1, then the contribution of shape function 1 will be more. If the point considered is closer to the node 2, then contribution of the shape function 2 will be more. This is called interpolation. When we say n1 pi 1, so this contribution will be more, right? n2 pi 2, for this point pi 2 contribution will be more. That is a linear interpolation, we can easily understand. And the second property is sum of all the shape function is equal to 1 always. So this property is useful for checking whether the shape functions are correct or not. When we solve the problem, we will use this property mostly. Sigma ni, mathematically sigma ni is equal to 1, where I varying from 1 to n, like that. Then total number of shape function. How many number of shape function will be there for a particular element? That is based on the total degree of freedom present in the element. So here we are using one dimensional line element, and we consider only two end node 1 and node 2. At each node we assumed 1 degree of freedom. So pi 1 and degree of freedom pi 2 like this. Totally 2 degrees of freedom. Total number of shape function will be degrees of freedom at each node, that is 1. Number of node is 2. So total shape function will be 2. Suppose if you assume 2 degrees of freedom at each node for the same element, in case of beam problem, truss problem we will have, there we will have more number of shape function, that is 4 shape function like that. So total number of shape function is based on the total degree of freedom present in the element. We will summarize what are the basic characteristics of an element. So before using an element, we should know all these characteristics, then only we can easily apply this element for any engineering application. So when we say element characteristics, we are listing these are the characteristics. First thing, we should know what is the shape. So here it is a one dimensional element, so it is a straight line element. Number of nodes, we are assuming two end nodes 1 and 2. So these are called primary nodes. Any node which is assumed inside the element is called secondary node, that we will discuss later on. So for higher order element we will have the secondary nodes also, that we will discuss later part. The number of degrees of freedom at each node. So here we are assuming only 1 degree of freedom. The common notation used here pi 1 pi 2, that is called field variable. In case of scalar variable problem, this pi 1 pi 2 may be temperature T1 T2 or pressure P1 P2 like that. In case of vector variable problem, the displacement may be u1 u2. When we use this line element for solving bar problem, we will use u1 and u2 in place of pi 1 and pi 2, because the u1 and u2 are displacement along the x direction. The field variable common notation is pi. Depends upon the application, we will have different notations. Total degree of freedom, number of nodes and multiply with the degrees of freedom at each node. So number of shape function will be equal to total degrees of freedom of the element. So these are the characteristics. So now after knowing these basic characteristics of this one dimensional line element, we are going to apply this line element for various engineering application. First we are going to start with the structural application. Then we will see thermal problem and the dynamic problem also. In the forthcoming parts, we are going to solve problems using this one dimensional line element. Thank you. Thank you for your patient listening.